Okay. Thank you for the kind introduction. Hi, I'm Haneul Kwak, working on the sodium cesium BEC experiment at WillLab. Today, I'm going to talk about our recent progress on the BEC of dipolar molecules, especially focusing on the expansion dynamics of a molecular BEC and its agreement with the mean field theory. So people are trying to realize the strongly interacting system, and we can characterize the interaction strength of the system using this dimensionless gas parameter, which is defined as the number density times the interaction length scale of the system. So for our familiar alkali BEC, it belongs to a somewhat weakly interacting system because the S-wave scattering length representing the interaction strength is small, and also the gas parameter is quite small. But on the other side, we have the most one of the most representative strongly interacting system, which is liquid helium with a pretty large gas parameter, around 0.121. And in the intermediate regime, we have our friends, dipolar atoms and molecules. And in these systems, we have another tuning knob, which is a dipolar length, representing the dipole-dipole interaction between particles in the system. And by tuning these two relative strength of these two interaction parameters, we can cover a wide range of gas parameters. So we have observed so many efforts of people to study strongly interacting system in these dipolar quantum gas. For example, when the dipolar interaction is smaller than the contact interaction, people saw this magnetostriction effect, where the dipolar Bose gas stretches to the B field direction. When the two interaction becomes comparable, people observe this long-sought supersolid state where the individual droplets are connected by a non-zero supersolid part. When dipolar interaction dominates, people found this self-bound droplet, which is a self-bound object that is not expanding even if you release the cloud from the trap. So without external confinement, this guy doesn't expand. And recently we found a totally new system, which is a BEC of dipolar molecules of sodium cesium. And we think this, in this promising platform, we can study more strongly interacting systems with tunable interactions. So to make a stable BEC, as we saw yesterday's talks, we need to use this microwave shielding technique to engineer the intermolecular potential. So this is what happens when we don't use any external field. So the intermolecular potential is attractive. So every two-body collision will lead to loss. But if you use these two microwave fields dressing the rotational transitions, one is the sigma field dressing the 0, 0 state to 1, 1 state, and the other field is the pi field dressing the 0, 0 to 1, 0 rotational transition. If we use these two microwave fields, the intermolecular potential becomes repulsive. So we can protect the molecules from getting too close to each other to get lost. And in our system, we have pretty large repulsive hardcore potential. We call this repulsive potential hardcore potential because it scales as 1/R6. So the hardcore potential radius is about 2,000 Bohr. So we also have another effect, which is a tunable dipolar interaction. So for the vertically oscillating pi field, we can recover the traditional dipole-dipole interaction between molecules. And for this circularly polarized sigma field, the dipolar interaction has exactly the same form, but with the opposite sign. So by tuning the strength of these two fields, we can, in principle, cancel out the long-range dipolar interaction and leave the system with this repulsive potential. So by doing that, we can extend our sample lifetime from like almost 10 milliseconds to 10 seconds, which is almost like 10 to the third times longer lifetime. It's about 10 seconds, so it's enough for most of the cold atomic or molecular gas experiment. So thanks to that, we were able to realize this BEC of dipolar molecules. So now we want to tune the dipolar interaction to study the effect of dipolar interaction. When we just use this perfect circular field for the sigma field and use the corresponding pi field balancing this sigma field, we have no dipolar interaction. And if we look at the cloud from the top, we don't see any distortion of the cloud. But once we introduce the elliptical field, so we can distort this perfect circular field into elliptical field. In this case, in this case, the molecules are mainly aligned to this major axis of the microwave field. So the induced dipolar interaction becomes attractive in this axis and repulsive in this axis. So that distorts the cloud in the microwave major axis direction. We can also quantify the unbalance of these two microwave fields using this parameter called ellipticity. So this is our full intermolecular potential in the XY plane. We have a very repulsive shielding core at the center, and we have attractive dipolar interaction in one direction and repulsive dipolar interaction in the other direction. So these two are the angular parts of the each interaction. This is a hard core potential. This is a long-range dipole-dipole interaction. So the next question is, does the mean field theory still work in our system? So in order to incorporate the real potential into our the mean field potential that can be used for Gross-P-Tepsky equation, what we need to do is we solve the scattering equation for the real potential. And thanks to the help of our two-body theory collaborator, Thijs, we can calculate the scattering length and use this G parameter for the contact interaction coming into this GPE. And also we can just import the long-range dipolar part to this long-range dipolar interaction for the mean field potential. So this is the mean field potential used for the GPE. And also here we are plotting the scattering wavelength and scattering length and the dipolar length as a function of the ellipticity. And for the long-range dipolar interaction, this is the angular part, and you can see from this equation, this has a very unique type of dipolar interaction, which is very different from the traditional dipole-dipole interaction. So now we can use the Gross-P-Tepsky equation treatment. So this is the kinetic energy, and this is external trap energy, and the last this integration term is the mean field interaction. But if we only include up to this mean field interaction term, what happens is actually for a strong dipolar interaction, stronger than the contact interaction, this GPE predicts that the BEC collapse because of the attractive part of the dipole-dipole interaction. But in such a strongly interacting BEC, we have another term, a higher order term representing the quantum depletion. So some particles are kicked out of the BEC and occupy some high-lying excited states. And this term is the corresponding higher order term that scales as the wave function cubed. And we call this term Li Huangyang term, naming after the people who made this term. So thanks to the, so this G Li Huangyang, this constant is always positive as long as the scattering length is positive. So thanks to this repulsive interaction, this term kind of stabilizes the BEC, resisting against the attractive part of the dipolar interaction. So we are also plotting this Q5 term in this G Li Huangyang term as a function of ellipticity. So yeah, because there's a possibly negative term in this integrand and in this bracket. If the dipole interaction is bigger than some interaction, we have this imaginary part. But people usually just ignore this small imaginary part in most cases. But in our case, when we do this integration, we just ignore the integral when integrand when the term in this bracket becomes negative. So this is the modified Q5 term denoted with this green line. It's a little different from the usual real part of the Q5 term. And please note that this Q5 term is 1 for non-dipolar BEC at 0 degree ellipticity. Okay, so then we have our theory prepared, and let's move on to the experiment. The sequence is pretty simple. So we load our crossed ODT with a non-dipolar BEC. And after that, in 200 milliseconds, we ramp up the ellipticity from 0 to the target value we are interested in. And after that, we release the cloud from the trap and let it expand for time of flight and monitor the expansion dynamics. In our BEC, we have 2,000 particles in the BEC, and the BEC fraction is more than 70%. And the scattering length is 2,000 Bohr radius at the 0 degree ellipticity. And we are using this circularly symmetric pancake trap to exclude any anisotropy coming from the trap and only focus on the anisotropy from the dipolar interaction. So in this non-dipolar case, the cloud doesn't show any distortion. So as you can see in this Gaussian radius as a function of time of flight, both axes expand at the same speed, the same size. So from the images, you can also see the cloud expands isotropically. But when there is a dipolar interaction, the cloud will distort in the strong microwave axis, which is an attractive axis. So the attractive dipole-dipole interaction axis expands faster, and the repulsive axis expands slower. So the fast expanding one is the attractive axis, and the slowly expanding one is the repulsive axis. Also, we are plotting the aspect ratio of the cloud as a function of time of flight. And for non-dipolar case, it's just consistently 1. And for a dipolar case, the aspect ratio is even just increasing without any aspect ratio inversion that is expected in non-dipolar case. And these solid lines are all coming from our EGP prediction, and we can see that these matches pretty well with the experiment up to some uncertainties in the trapping frequencies and imaging resolution. So we also show these images for images at 20 millisecond time of flight for a range of different ellipticity. And from this experiment, you can see the cloud distorts more and more as you increase the ellipticity. And suddenly, after a 3.5 degree ellipticity, the cloud starts shrinking. So we are observing a transition from a BEC to a droplet phase. And also we show this EGP images corresponding to each ellipticity, and it's now becomes more clear that after 3.5 degree ellipticity, it forms a very thin and dense object. But it's not a fair comparison because we have our imaging resolution, finite imaging resolution. So what we do is we blur this the raw EGP images with the Gaussian blurring of the radius of our point spread function in our imaging system. So now we can compare the first row and the third row. And by eye, it's very similar. Also, from the aspect ratio of the cloud, the error band is coming from the EGPE. And it also matches pretty well with the experimental data up to 3.5 degree ellipticity. But after 3.5 degree ellipticity, it starts deviating. Yeah, and the error band is coming from some uncertainties in the pi field calibration. Yeah, so this brings me to the end of my talk. As we have finite imaging resolution, we are planning to install a high NA objective because, so in the EGP simulation, the in situ density, we can sometimes see for a certain degree ellipticity, these two droplets are connected by a non-zero superfluid part, which is very suspicious to have supersolidity properties. So once we get a high NA objective, we can directly image the in situ profile of the gas to see there's a really a link between the droplets or not. Also, we can check the time of flight interference pattern of these cases to see if the interference pattern stays the same or not for different experimental runs. We can also even do this dynamic interaction tuning. If we change the orientation or the strength of the dipolar interaction, we can steer the BEC to generate the vortices or to probe the superfluid properties. So I would like to thank the whole team, including our theory collaborator, Thijs Carmen, and thank you so much for the attention, and please let me know if you have any questions. Yeah.
Really nice results. In the interest of time, perhaps one question from the audience? Yeah.
Thanks for the wonderful talks, really great results. I have a question about alternative detection methods. Sometimes it would be very nice to really measure the momentum distribution of your system after you do something with the system. But for that, I suppose you would like to switch off everything. Also that contact part. Can you do that? Or can you modify your detection in some way that you really faithfully measure the momentum distribution?
Yeah, that's actually a very good question. But so from theory calculation, we optimize the shielding parameters for example, the detuning and the power for each microwave fields. So as long as the shielding quality stays good, we can go down to like 1800 Bohr radius for the scattering length. Yeah, but we cannot go below that number. So yeah. So there's no known way to reduce the scattering length to 0, actually. Yeah. So if you do the time of flight, there's always the interaction effect, so it will so the resultant time of flight images is not exactly the Fourier transform of the in situ density image. Yeah.
Let's thank the speaker again.